Welcome to our AI project. In this video, we will explore how artificial intelligence can be used to prioritize tasks using machine learning and object-oriented programming. Let's dive into the journey from theory to code and see how AI can help us stay organized and efficient. This lesson combines theory and a real-world project. Our focus is on AI applications, specifically how to build a model that can look at tasks and predict which ones are most important. It's a great way to learn both programming and practical AI. Here's our roadmap. We'll go through 7 key steps: defining the goal, collecting training data, pre-processing the data, training the model, testing it, integrating it with our OOP code, and finally using it in practice. Each step builds toward a smart system that can help us manage tasks. The first question that we should ask is, what do we want? We want an AI model that can look at a task and predict its priority. For example, finishing an assignment might be high priority, while grocery shopping could be low. The model will learn to make decisions based on examples we give it. Each example is a task with features like importance, estimated time, and deadline. The label is the priority level, like high, medium, or low. These examples teach the model how to recognize patterns. Before training, we need to prepare the data. For deadlines, we calculate how many days are left. For priority labels, we convert words into numbers like high equals 2, medium equals 1, and low equals 0. Machines don't understand words, so we speak their language, which is numbers. Now we train the model. We'll use a simple machine learning algorithm like decision tree. A decision tree regressor is like a game of 20 questions, but instead of guessing an object, it tries to predict a number. Here's how it works step by step. First, we split the data. The algorithm looks at your data and finds the best question, like is age less than 30? This way, it split the data into 2 groups, where the target values are more similar within each group. Then we keep splitting. Each group is then split again with new questions, like is salary more than 50,000? The tree keeps branching until the groups are small enough or similar enough. Then we make predictions. For a new input, you drop it down the tree by following the yes-no questions until you reach a leaf node. At the leaf, the model predicts the average value of the training data that landed there. Here's a concrete example. Suppose you are predicting house prices. For the first split, we ask the following question. Is the house bigger than 100 square meters? If yes, next question, is it in the city center? If no, next question, does it have a garden? At the end of the path, the tree says houses like this cost around $200,000. So in short, classification tree predicts a category like spam, not spam. Regression tree predicts a number like house price. Then we feed the algorithm the features and labels and it learns patterns. Think of it like teaching a student. If homework is due tomorrow and it's important, do it first. After training, we test the model with new tasks it hasn't seen before. If it predicts well, we know it's ready. It's like giving our students a quiz. Can they tell which task is urgent based on what they have learned? Next, we connect the AI model to our task class. When we create our new task, we convert its details into features, send them to the model, and store the predicted priority. It's like having a smart assistant that tags your tasks as do now or later. Finally, we use the system. We create tasks with title, deadline, importance, and estimated time. The AI predicts the priority, and our task manager sorts and displays them. Your planner now automatically highlights what's most urgent thanks to AI. Now that we understand the process, it's time to code. We'll build the task class, train the model, and connect everything together. By the end, you will have a working AI-powered task manager. Let's get started. We start by importing two libraries, sklearn and NumPy. From sklearn.tree import DecisionTreeRegressor. Import NumPy as an NP. The first one gives us access to a decision tree regressor, which is a simple machine learning model that can learn patterns and make predictions. The second helps us work with numerical data efficiently. Now we define our first class. We call it task, just as we did before. This is the blueprint for each to-do item. It groups related data like title, deadline, etc. into one object. Then comes the constructor, def _init open parenthesis self title deadline importance, and we set it to 1, then estimated time, and we also set it to 1. This is the default value. Okay, this method runs automatically when we create a new task. It attaches attribute to the object. Inside it, we write self dot title equals title, self dot deadline each task gets its own title and deadline. We also assign default values for importance and estimated time. Both default to 1 if not provided. And we set the status to incomplete, meaning the task hasn't been finished yet. Let's talk more about the two numbers we see in our class task, which are importance and estimated time. Think of these as the descriptive features of each task. Importance tells us how critical or urgent a task is. For example, finishing a project report might have an importance of 5, while the laundry might only be a 1. Estimated time tells us how long the task will take. Maybe grocery shopping is just 1 hour, but exam review could take 10 hours. Now in machine learning, features are simply the input we give to a model. They describe the thing we are trying to make predictions about. So when we build our feature matrix, every task is transformed into a small pair of numbers, its importance and its estimated time. Once we have these pairs, our machine learning model takes them in, and based on what it learned during training, it predicts a priority score. So remember, importance and estimated time are not random values. They are carefully chosen features that describe tasks. The model then uses those features to decide which tasks should come first. Next, we define a class to manage multiple tasks. We call it TaskManager. They separate responsibilities. The task class handles individual items, while TaskManager organizes them. Inside it, in itself. Okay, then we start with an empty list called tasks. This list will hold references to task object. Now we define a method to add a new task. It takes the same argument as the task constructor. Inside the method task, then we give it title, then self dot tasks dot append, and we give it task. Okay, so we create a new task object and append it to the list. Now the manager remembers that task. Now let's add a method to list all tasks. This method loops through the task list and prints each one. So we use an F string to format the output. Each task shows its title, importance level, estimated time, and current status. Now comes the exciting part, machine learning. Here we define a method to prioritize tasks using a trained model. This method takes training data. X_train is a list of features, in this case importance and estimated time. Y_train is a list of target values, which is the priority scores we want the model to learn. Now, inside the method, we create a decision tree regressor. Let's leave a comment to explain this part of the code. This creates an instance of the DecisionTreeRegressor class from sklearn. At this stage, the model is just an empty decision tree. It hasn't learned anything yet. Then we train it using the provided data. Model.fit x_train y_train. This trains the model using your training data. X_train for features, Y_train for target values. The algorithm builds a decision tree by recursively splitting the data based on feature values to minimize prediction error. After calling .fit, the model now contains a trained tree structure that can make predictions. Next, we prepare the features for our current tasks. This line is built in a NumPy array from your list of tasks. To make predictions, the machine learning model needs these same features it saw during training, which are importance and estimated time. So these are our actual tasks, not the training data. We still haven't provided the training data yet. Here we have list comprehension. It loops over each t in self.tasks. So self.tasks must be a list of task object. For every task, it makes a small list with two values, importance and estimated time. The result is something like this. np.array converts to NumPy array. It turns that list of lists into a NumPy 2D array or a matrix. Each row corresponds to one task. Each column corresponds to a feature. So here there are 3 rows. Each row has 2 features. This one is column 0 and this one is column 1. Column 0 corresponds to importance and column 1 corresponds to estimated time. So the same applies to the second row and the third row. X_tasks is now a feature matrix shaped the number of tasks by 2. So here there are 3 rows. So the number of tasks is 3. And by 2, it means there are 2 features. For example, if you had 4 tasks, it may look something like this. In short, X_tasks is the input features matrix for machine learning, where each task is represented by importance and estimated time. Then we predict the priority scores. This line is where our trained model makes predictions for each task. That is, it gives us a score for each task. Higher scores mean higher priority. Model is your trained decision tree regressor or whatever machine learning model you used. The predict takes a feature matrix, which is X_tasks, where each row represents one task with its features. The model uses the decision tree built during training to compute an output value for each row. As I said before, this is a 2D NumPy array with shape, number of tasks by 2. So the output is the priorities. So predict returns a NumPy array of predictions. Each prediction corresponds to one task, same order as x underscore tasks. If the model was trained to predict a priority score, then okay, so here we have rows, okay, there are 3 rows, okay, and 2 columns. So each column corresponds to a feature, importance and estimated time, and these are the priorities. For example, the first score here corresponds to the first column, the second score here corresponds to the second column, and the third score here corresponds to the third column. So now you have a list of predicted priorities, one per task. This was just for the sake of illustration. So now you have a list of predicted priority values, one per task. Then we pair each task with its predicted score. So zip here combines the two sequences element by element. I mean elements from self.tasks and priorities. List turns the zipped pairs into a list of tuples. Then we sort the list in descending order. This ensures the most important tasks appear first. That is, the tasks are sorted by their predicted priority. Highest first. Key equals lambda x semicolon x1 tells Python to sort by the second element of each tuple. Reverse equals true, sort in descending order, highest priority first. For example, before sorting, we might have these results. Task 1 might be 7.2, task 2 3. And task 3 5.0. So after we sort them, we get 7.2, 5.0, and 3.5. It means it has been sorted in descending order. Finally, we print the prioritized list. So this line of code prints a header with \n adding a blank line before it. For task score in tasks with priority, it loops through each tuple, which contains task and its priority score. This line of code prints the task title and its priority score formatted to 2 decimal places, as we see here. Now let's look at the main section of the file. This line tells Python only run the code below if the file is executed directly, not imported as a module. Inside it, we create a TaskManager. Then we add 3 tasks. Each task has a title, deadline, importance level, and estimated time. We also define training data. This data simulates how importance and time relate to priority. For example, a task with importance of 5 and time of 5 has a priority of 10. Here we defined our training data, but notice it's just dummy data. With only 3 examples, it isn't nearly enough to train a real machine learning model. These numbers are simply placeholders meant to show how the code works. In practice, we would need a much larger and more realistic data set to get meaningful predictions. Finally, we call the prioritization method. The model ranks the tasks and print them in order of predicted priority. So now let's run our Python file and see. Oops, here we got an error. Let me see. Model.oh, here there must be it seems to be a typo. Okay, predict. Let's run it again. And here we got the result. So prepare project, the priority score is 10, so it is sorted the highest, and finish homework with a priority score of 7, so it is the second, and buy groceries with a priority score of 3, so this is the third most important task to do. Let's walk through what's happening in memory step by step. We create a TaskManager object. Inside it, the tasks list starts out empty. Each time we call add_task, Python creates a new task object with its own attribute. The managers list stores a reference to the object. Then we train a decision tree model using sample data. We use it to predict priority scores for our actual tasks. Then we pair each task with its score, sort them, and print the result. Python handles all of this behind the scenes, moving between object, list, and method calls. And that's how you build a smart task manager using Python and machine learning. You can expand this project by adding deadlines, categories, or even a graphical interface. The possibilities are endless.